So, all right. So I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day again. I thank you for the students. Just ask you to just give us insight today. Help us to understand a little bit more about differential equations together, Lord. In your name I pray, Lord Jesus. Amen. So we'll look at the solution to that quiz you guys just took. Surprise attack mission. A little bit later, hopefully. And if you don't get it at the moment, that's okay. But I hope that, once you're done studying a little bit more, that quiz will become easy to you. I'm hoping. Not yet, obviously, but here's the question. How do we solve this problem? This is three differential equations and three unknowns. So how do we solve this? All right. So we're looking at, so convert it to the matrix problem, right? So we've got x, y, z prime. And the matrix is easy enough, right? It's just, it's all ones, right? All right. So this is my coefficient matrix A, right? So for those of you who've had 221, or maybe are currently taking it, or maybe you just remember stuff from high school, whatever. What can you tell me about this matrix? Is it invertible? Is it not invertible? What do you think?
Is it invertible?
Invertible. Ooh.
No, it's vertical.
Oh, not invertible. Yeah, so not invertible, right? Because it has a repeated column or row, right? So there's clearly a dependence amongst the columns, and so that tells me the determinant of A is 0. But the other thing I know about the determinant of A, guys, is that the determinant of A for a 3 by 3 matrix, here's just some fun linear algebra for you. It's the product of the eigenvalues possibly repeated. So if this is equal to 0, then I can anticipate one of my eigenvalues will be 0, all right? This is very helpful as we're working out the problem because we kind of know what we're looking for, all right? All right, so let's work out the characteristic equation. Now, do you guys want me to use lambda? I could use x instead. We don't have to use lambda. Lambda? All right. A minus lambda I it is then. So we got to look at the determinant of 1 minus lambda. 1, 1, 1, 1 minus lambda, 1, 1, 1, 1 minus lambda. This is the part of the eigenvector calculation that is most important to be really, really careful with. Don't be like me when I tried to work this problem out in Math 221 the other day, and I foolishly made a mistake. Actually, the bigger mistake I made that day was not plugging in my mic. Wait a minute. All right, good, mic working. Just checking. So 1 minus lambda, right? And then minus 1 times the determinant of 1, 1, 1, 1 minus lambda. Plus 1 times the determinant of 1, 1 minus lambda, 1 and 1. All right. This is not the greatest example for learning determinants from, right? But it is somewhat forgiving in terms of copying like the pattern down. Now, all right, so this first one, we've got 1 minus lambda times parentheses what? Well, I could write that as lambda minus 1 quantity squared minus 1. And then I have minus parentheses 1 minus lambda minus 1 plus parentheses 1 minus parentheses 1 minus lambda. All right. Just to emphasize where things are coming from, we've got this is that. This piece is that piece. And this one is that one. All right. All right, so let's work it out. We have 1 minus lambda times what? Well, this is lambda squared minus twice lambda, right? And that's it. See, because I get a plus 1 and then a minus 1, the 1 and the minus 1 cancel inside that bracket, right? How about this here? 1 and, see that? See that cancellation? So what are we left with? Minus and minus plus lambda, all right? Minus and minus plus lambda. All right? So, in fact, there's a lambda everywhere here. We could factor it out. Lambda times 1 minus lambda times lambda minus 2 plus 2. All right? So I factored a lambda out of this piece right here. See that? And these two guys gave me that. All right, let's work it out then. What do we got? Lambda times, well, I'm just going to FOIL it out. So that's lambda plus 2, excuse me, not plus 2, minus 2, right? Lambda minus 2 minus lambda squared plus 2 lambda plus 2. Oh, what'd I do? Yeah.
Are you factoring out a lambda from the 1 minus lambda?
No,
Of the term?
I'm factoring the lambda from here.
Gotcha.
So those, I mean, this is coming from this as well as that.
I'm just not sure because the 1 minus lambda that multiplies that. Oh yeah, never mind.
Mm-hmm. Okay.
Don't mind me.
That's all right. I mean,
Problem solved.
we'll see if we mind me in a second here. All right, so these 2's cancel. I have a healthy respect for this problem. It got me yesterday. All right, so that's 3. So I have lambda times 3 lambda, because I got 1, 2, 3 minus lambda squared. So I can factor that, and that gives me lambda squared times 3 minus lambda. All right, so we find that lambda 1 is equal to 0 twice, right? That's a double root. And we find lambda 2 is equal to 3, just once, right? This twice and once that I'm speaking of, these are the so-called algebraic multiplicities. All right, algebraic multiplicities. That's the number of times that the eigenvalues appear in the characteristic equation. All right. Now, the theory of linear algebra says that you can have as many eigenvectors, independently speaking, as the algebraic multiplicity, but you can't have more. And there's always at least one eigenvector for each eigenvalue. That much we can be sure. Now, getting this repeated eigenvalue of 0, it may or may not be the case that we actually get 2 independent eigenvectors. We'll have to see. We have to work it out. All right. So let's work on that then. Which one do you guys want to do first? The 3? Or what's that, the 0? All right, lambda 1 equals to 0. So we're looking at a minus 0 times the identity times a vector, right, equals to 0. So specifically, that's 1, 1, 1, 1, 1, 1, 1, 1, 1 times u v w equals to 0, 0, 0. Can we solve this? It's kind of dumb, isn't it? I mean, there's not much to do here linear algebra-wise, because if you think about it for a second, you realize there's nothing you can do except accept the fate that you only have one equation to work with, right? It's just in your face. We have the same equation 3 times, right? So like, let's write it down. So this tells me, okay, so apparently W is equal to like minus U minus V, right? Fine, I'll do one more step here. U plus V plus W equals to 0, right? And from that, I can get to W is minus U minus V, all right? Which gives me that my vector that I'm looking at has the form like U, V, and minus U minus V, all right? So if I factor out the U, that gives me 1, 0, minus 1 for this one, plus V times 0, 1, minus 1. So, question. These two vectors here, are these independent? Are these linearly independent? What did we say about two vectors? They're linearly independent if what? They're not multiples of one another. Can those be multiples of one another? Surely not, right? I mean, one's got a 0 and a non-zero. I mean, just look at the x component, right? One's non-zero, the other one's 0. You can't create non-zero from 0. They're not multiples of one another. Therefore, they're linearly independent. So in this case, hooray, we found two eigenvectors, all right? And so we can use, so yes, answer my question. Yes, they are. And as such, we can build two independent solutions from those, going back to our eigensolution, right? So like, we get solutions, R1, let's say, equal to e to the 0 times t times, 1, 0, minus 1. And R2 equal to e to the 0 times t, which is kind of dumb to write, right? But there it is, 0, 1, minus 1. Of course, I mean, these solutions are just what? These are constant solutions, right? It's simply, this first one, we can simplify it. It's just 1, 0, minus 1. And the second one is just 0, 1, minus 1. In other words, two ways you could solve this system of equations is simply to put x equals to 1, y equals to 0, and z equals to minus 1. You'd solve all three of the differential equations, right? Or you could put x equal to 0, y equals to 1, and z equals to minus 1. That also would solve this system of differential equations. Yeah? So there's two independent solutions. Now lambda equals to 3. That should be different. So we got a minus 3i times u2. Let's say, I guess I should say u3 because I really want to think of this as my u2, u1, and I want to think of this one as my u2 if I'm numbering them, Anyway, so I'm looking for u3. So a minus u, what's a minus 3i? Well, that gives us minus 2, 1, 1, 0, minus 2, 1, 0, 0, minus 2. How'd I get those zeros there? That's crazy. What should those be? A minus 3i. Does it give you zeros down there? No. All those are ones. All right. So we're trying to solve this. Listen, there's two ways to solve an eigenvector problem. The one way is to do the math. All right? The other way is just to guess. So I can do the math here, or I could just try to solve a times u3 equals to 3 times u3, right? So really, I'm just trying to solve 1, 1, 1, 1, 1, 1, 1, 1 times uvw equals to 3 times uvw. Sometimes it's easier just to solve the one on the right by guessing. Can you guess the answer? I mean, if you can't guess the answer, you got to work out the equations, all right? Can no one guess? I really don't want to do the algebra. You want me to do the algebra? We can do the algebra. So probably the best way to do the algebra like this is to do what are called row operations. But since I don't want to get into all that, we can just like, let's number these equations 1, 2, and 3. All right. And you guys tell me what happens if we take, say, equation 2 minus equation 3. What's that give us? In other words, we take u minus 2v plus w minus u plus v minus 2w equals to 0. That gives me what? The u's cancel. We get minus 3v plus what? Plus 3w is equal to 0. So apparently, we could put w equals to v. Now the theory of linear algebra is helpful here. I know that there's a unique solution to this problem. Not a unique. I know that there's just one parameter in the solution set because we already have two linearly independent eigenvectors for 0. So another part of the theory is that the algebraic multiplicity is the maximum number of linearly independent eigenvectors you can get. So since I only have a multiplicity of 1, I'm just looking for one parameter in my solution set. See, I had two parameters in the solution set for the equal to 0 eigenvalue. But that can't happen here because they've just got repeated once. So pretty much, once I get this, I can kind of just go, oh, okay, well, I know I can put w equal to v. So go back to either one of the equations. Like, let's go to the third one. The first one, we haven't used that one yet. So minus 2u, right, plus v plus w equals to 0. And I can solve that for, like, 2u is equal to v plus w, right? Which, by the way, is just 2v. So apparently u is equal to v is another nice thing to know. All right, let's put it all together then. We're going to use v as my parameter. And let's choose v equals to what? 1. Very good. You guys are getting it. So then my vector, u3, is 1, 1, 1. Now if I go back to the question and ask you, guess a vector that's 3 times itself, it becomes like, oh, I should have seen that. Right? Once you know the answer, it's easy to see it, right?
Is it any multiplier, or is it just certain multipliers?
Well, but you see, I mean, if I put this here and I multiply, I get 1 plus 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1, I get 3, 3, 3, which is 3 times 1, 1, 1. If I used 2, 2, 2 for my vector, I would have gotten, 6, 6, 6, which would have been 3 times 2, 2, 2, That's just a choice.
Gotcha.
So let's put it all together. The general solution then is as follows. R of t is equal to C1 times my handy-dandy constant solution, 1, 0, minus 1, plus C2 times 0, 1, minus 1, plus C3 times e to the 3t times 1, 1, 1. And there you go. That's the general solution to this system of differential equations. All right? So if I was teaching this class like, Tuesday, Thursday, I'm more inclined to just let you guys solve this in its entirety on the test. And here, I feel like I probably give you a hint. Something like, hey, by the way, the vector 1, 1, 1 is very interesting. If I do that, that makes this problem pretty easy, relatively speaking, right? Like finding U1 and U2, that's pretty straightforward. The finding the U3, well, okay, that's a little bit more involved, but you know, you guys probably need some practice on those, right? So let me show you something here. So what I'd like you guys to do is to work on solving the eigenvector problems, right? Maybe work through the ones in the notes. See if you can reproduce my results. Well, because like I'm sure you need to work on them, right? Surely.
Don't call me Shirley.
I guess I walked into that. Let's see here. So if you look in the notes, though, I have where I'll start Monday is just to Monday. I'm not going to work them out. I'm just going to show you results Monday, starting with, and I'm going to show you that there are some problems where eigenvector solutions are enough, and there are other problems where eigenvector solutions are simply just not enough. All right. We need something else, and that something else is the matrix exponential, which I will introduce Monday. So just to end class, this is what you're supposed to do for problem 1. That was the reduction of order idea. All right, just that. Problem 2, I gave you eigenvectors with eigenvalues 6 and -7, so you just write down the answer, done. For problem 3, I gave you a complex eigenvector with complex eigenvalue 7 minus 4i, so you write down the complex solution and work out its real and imaginary parts, or you could use the a plus ib formula that we had. There's the answer. And for problem 4, you just work out the characteristic values are actually 5 and 6, and so we get, and by the way, how am I solving this equation? Do you guys know? Let me tell you my trick. I guess. And my guess is really stupid because all you have to do is pick a vector which is perpendicular to this one. So the simple thing to do is swap the numbers and put a minus on one. That will automatically be perpendicular to this and that. So I just 1, 2 swap and put a minus on one of them but not the other. Then it dot products to 0. Same thing down here. I just want it to be perpendicular to both rows, which is the same thing, scalar multiple, so I just do like 1, 3 with a minus on one of them, and that'll work. I don't even actually have to think about the two equations, two unknowns, if I just see it. Now you can't always do that for the 3x3 problem, right? Although if you look at the one we did today, you could do that for the lambda equal to 0 pretty easily. And maybe even the other one. But there you go, that's the general solution. And with that, you may begin your weekend. Woohoo! So you guys can do these problems. These problems are not hard. Everyone can do these problems. Maybe not today, but soon.